Hey y'all, today we're going to kind of summarize our intermolecular and interparticle forces unit by looking at a laboratory technique known as chromatography. Now, we've talked about other techniques of separating molecules based off of differences in their properties. So we can use distillation or evaporation to separate things based on their boiling points. We can use filtration to separate things based on their phase. But what happens if you have something which only differs, relatively speaking, in their interparticle forces? This is where chromatography can come in. We use chromatography to separate different substances based off of their relative interparticle forces. So let's go ahead and take a look at the two types of chromatography that we use and how they differ, but also how they are very similar in a lot of ways. Let's get started with thin layer chromatography. Now, thin layer chromatography, sometimes also known as paper chromatography, is going to be able to separate things based off of their relative polarities. But something to be aware of is you can't actually collect a sample, or at least a large sample, of the material when you do this. So it's really good for analyzing the presence or absence of different substances, but it's not very good at actually purifying a substance or collecting a uniform sample of a substance. Now, in thin layer chromatography, we have two phases. There's the mobile phase, or the solvent, and the stationary phase, which is going to be our target substance. The way it generally works is we dip a piece of paper, chromatography paper, into our mobile phase, our solvent. Now, the solvent can be either polar or nonpolar. Normally, it's nonpolar. However, it could be a polar substance too. So let's just say it's hexane, all right? So we've got mobile phase, which is hexane. Now, hexane, being a nonpolar substance, is going to experience mostly intermolecular forces of London dispersion forces, okay? It's not going to experience dipole-dipole forces, and it's not going to experience anything beyond that. The static phase, or the stationary phase, meanwhile, we don't know what it's going to experience. But what's going to happen is through capillary action, the hexane is going to move up the thin layer, up the paper. As it does so, it's going to move past our target substance. This is the stationary phase. As it moves past that substance, the molecules of hexane are going to interact with the molecules in the stationary phase. Now, if there are multiple molecules present, each one is going to move differently up the paper depending on how it interacts with the mobile phase. The more strongly it interacts with the mobile phase, the more distance it's going to travel up the paper. When we allow this experiment to run for a specific amount of time, we can then analyze how far the solvent front has moved. So that's basically how far up is the paper wet, and then how far did it carry each component of our stationary phase. The further it carried the stationary phase, the more like the stationary phase it is. So in other words, a component that moves further up the paper would be more similar to hexane in that it experiences more London dispersion forces, whereas a stationary phase component that moves less far up the paper is going to experience less of those interactions and will likely be more polar as a result. Now, we can actually do a calculation that allows us to see this in a numerical way. It's called the retention factor, or RF value. You're not going to be asked to do anything with these RF values necessarily, or even calculate them, but it's an important thing to understand that the RF value is calculated by dividing the distance the compound traveled by the distance that the solvent traveled. So if they both traveled the same distance, then it would be a RF value of 1. If the solvent traveled 90% of the distance of the solvent, then it would be an RF value of 0.9. The greater the RF value, the more like the solvent that the compound is. So like I said, thin layer chromatography has benefits of being able to identify the purity of a substance and also understand the different components of a substance. However, sometimes we need to actually get a sample or purify a compound down into its component parts. This is actually often used in medicine, in food industry, and very frequently needs to be really well maintained and managed. We need a very pure sample in order to be food grade or medical grade. In order to do this, we use a system called column chromatography. Column chromatography uses many of the same features. It uses a stationary phase and a mobile phase. But instead of simply allowing a substance to passively travel up a thin layer, we're actually allowing it to filter down through a column, and as such we can collect it based on how it moves through that column. So in a column chromatography system, the way it works is this. The mobile phase acts as the solvent. It can be added at the top of the column and it filters down. As it goes to work, it's a process called elution, E-L-U-T-I-O-N, and it can act as the eluting agent, all right, which causes the elution process. Now, elution is removing the unwanted components, right? So we want to collect a very specific sample, so we remove the unnecessary components. Then in column chromatography, the stationary phase is the big difference. The stationary phase in column chromatography is actually a substance which is going to interact with the particles in a differential way based on the polarity of the particles. So the stationary phase is often made of non-reacting or inert chemicals that are really stable and don't break down easily. Okay? They're also generally very small. And so as a result, what's going to happen is all of the particles that are moving through the stationary phase are going to have to interact with the stationary phase itself. It's very important that the stationary phase interacts with some particles more and other particles less based on their polarities. But at the same time, we want the particles to move relatively freely through the stationary phase. So engineering a stationary phase is actually really important in column chromatography. But that's not as much for this class. That's more for analytical chemistry or a future chemistry class, or if you ever go into industry, the industry that you're in. We're going to focus on the process, though, which is very similar in the sense that there is a retention factor of column chromatography. And just like in thin layer chromatography, the retention factor tells you how similar the molecule is or the particle is to the actual stationary phase and the mobile phase. In column chromatography, the RF values are going to dictate when the actual substance leaves the column. So the more the higher the RF value, the faster it evacuates the column, it leaves the column because it moves with the mobile phase, and the lower the RF value, the later it moves through the column. And so what we can do is actually separate different compounds based on their relative RF values. So substances that have similar RF values are going to come out of this column at very similar times. But the nice thing is when we're purifying substances, that's going to give us a very pure substance because RF values are a very unique trait to especially medical or food-based compounds. All right, so that wraps up today's video. Today we looked at column and thin layer chromatography. Remember, the technique of chromatography itself is important, but so is being able to analyze chromatography results. In thin layer chromatography, remember, the further the target travels up the thin layer, the closer it gets to that solvent front, which is the distance the solvent traveled, the more like the solvent it is. So if the solvent is nonpolar, the further the thing traveled up the thin layer, the more nonpolar the target is. Similarly, something that travels less far up the paper is going to be more polar in that circumstance, less like the solvent that you used. Okay? Remember, solvents don't have to be nonpolar. Our example it was, but solvents could also be a polar molecule, and you need to be really careful about the identity of the solvent before you make any determinations. In column chromatography, the big benefit is that we can collect pure samples of substantial volume, okay? Whereas in thin layer we couldn't. A lot of the similar features, though, which is the fact that we still have a stationary and a mobile phase, and there's still a retention factor element, okay? The big difference is simply how we are going to run the experiment. What you need to take away from chromatography, though, is going to be the interactions component. How the two particles will interact with each other, which is going to tell us that RF value, which is going to tell us how we can separate the molecules using chromatography. And remember, chromatography is not the only way to separate molecules based off of interparticle forces. Evaporation, distillation are also ways to be able to collect things based off of relative interparticle forces. Both of those happen to be due to the ability to boil at different temperatures. So that's it for this video and the unit. I hope you enjoyed it, and I'll see you in the next one.